Nosotros no nos estamos yendo, sí. No, sí, claro.
Hi, everyone. Thank you so much for joining us today for the 5th webinar in the UFFCS America, Latina, and FOCO series from the IEEE-UFFC Latin America Initiative. Again, I wanted to reiterate before we get started that this webinar will be recorded. We're excited to have you join us today for today's topic, a look at history of internationally recognized Colombian timescale, UTC, and optimal clocks with trapped ions. Give me one moment while I pull up my other video for us.
América Latina en Foco.
We are now going to introduce our speakers, and while we do that, we invite you to participate in our poll questions. We will have, for this webinar, a talk will be given by our early career speaker, Milena Guevara Birch, followed by our other speaker, Liz Hernandez. And moderating today's session is Marina Gertzwolf. During the webinar, please type your questions in the chat box at any time. They will be answered during the Q&A session of this webinar. If you would like to ask a question during the Q&A session, please raise your hand and you can switch on your camera and unmute to ask a question. We will have an interpreter for today's session. At the bottom of your screen, you can press a button to enable this feature. My colleague, Hermes Camimeri, will go into further detail on how to use this feature.
Hello, everyone. Welcome to our 5th America Latina in Foco webinar. It's very exciting. Today we have this frequency control topics, amazing topics to discuss. And just before we start, you may see in the bottom of your screen a button, a feature called interpretation. So if you press that button, you will be able to choose off, English, and Spanish. So if you prefer to hear everything in English, just choose English. And if you prefer to hear in Spanish, please press Spanish. Don't leave it off. Keep English or Spanish, otherwise you will not hear some of us speaking.
Wonderful, thank you. I would now like to introduce the organizing committee of the Latin America Outreach Initiative, and it includes Hermes Camimura as the Latin America Outreach Initiative Chair. We also have Sophie Morse joining us as our Volunteer Engagement Committee member. We also have Andrea Polido as our Latin America Outreach Initiative volunteer. We also have Patricia Cordozo de Andre as our other Latin America Outreach Initiative volunteer. And then we also have Stephen Lee, who is in charge of our video editing services.
Okay, so do you mind sharing the announcements, please?
Of course. Give me one moment, please.
Yeah. We have our nice logo again. I think we can also launch the poll results if you don't mind, because this is on my screen here.
Sure.
Yeah. And okay, so if you missed any of our previous webinars, they are all available on YouTube, and the links are in the chat box. Andrea will be sending the comments there. You can read and see later. The next slide, we have, can you go to the next? We also launched recently this week, if you didn't watch, it was I think on Tuesday. We had our UFFC Society webinar series called Virtual Lecture Education Series. And if you missed this webinar, they will be also available on YouTube. But for now, I want you to just make sure you write down in your calendar our next webinar happening February 1st, 2022, with Dr. Michael Tobar, who will be speaking about precision metrology. And the link for registration is also in the chat box. Next slide, please. And now I would like to invite our UFFC student representative in frequency control, Etienne Batori, from University of Neuchâtel in Switzerland. And he will be speaking about volunteer work and his role in the society. Thank you.
Yes, thank you very much. So I am Etienne. I am the junior student representative for frequency control, and I'm here to explain to you how, as a student, you could be involved in the society if you want to. So to my understanding, there are three ways. The first way is to become a student representative. So there are 2 students per UFFC branch on a junior-senior logic. And the main task is to organize activities during the conferences. So ISAF, IFCS, IOS. This is a great opportunity not only to understand how these conferences work and how they are organized, but this is also a great, I have to say this, networking opportunity, as all the people that organize these conferences have great academic or industry achievements. There is a second way you can be involved in the society, and this way is to apply directly to open opportunities. I have listed the ones I have found yesterday morning on the UFFC website. And if you have a look at number 3, you can see frequency control junior student representative. So if next year you want to work with me, you can apply and have a chance to become a student representative. I would be very delighted if you wanted to do so. And the last way you could be involved is to apply to the so-called student task force on the same website. The idea is that you tell who you are, you tell what your interests are, and given the coming opportunities, UFFC will contact you. I can give you an example. Before COVID, the conferences were 100% in person. During COVID, 100% virtual. After COVID, they will be hybrid. So we will do both at the same time. So there is a good chance that we, the student representative, will seek for help during the forthcoming hybrid conferences because it will be tough work. So that's all for me. Thank you very much.
Thank you so much, Etienne. And it was great. I really recommend you to join this student representatives. They are very nice. They will explain you how the society works, and they will give you nice tasks to help with the society. And for you that just join us, you will see an interpretation button in the bottom of your screen. Please make sure you choose either English or Spanish to make sure you can hear all of us speaking. And now I will hand it over to Sophie. Thank you all for being here and enjoy the talks.
Hello everyone, thank you Hermes. So I'm going to introduce you to our first speaker for today, Milena Guevara Birch. She did her bachelor's and master's at the University of Costa Rica, and during her master's program she worked at the Centro de Investigación en Ciencia e Ingeniería de Materiales in the implementation of trapped atoms in optical lattices to study surface layers. She's currently doing her PhD in quantum optics and spectroscopy in the group under Rainier Blatt and Christian Roos at the Institute for Quantum Optics and Quantum Information in Innsbruck in Austria. Her focus is mainly on developing optical clocks with trapped calcium and aluminium ions. So with that, I'll leave you to enjoy her talk. Thank you.
América Latina en Foco.
Buenos días, mi nombre es Milena Guevara, vengo de Costa Rica, lugar donde hice mis estudios de bachillerato y maestría. En estos momentos me encuentro en Innsbruck, en Austria, haciendo mis estudios de doctorado en el grupo de óptica cuántica e espectroscopía bajo la supervisión de Rainer Blatt y Christian Ross. Mi trabajo de doctorado está basado en el desarrollo de relojes ópticos con trampas de iones. Me gustaría llamar la atención primero que un reloj óptico es un tipo de reloj atómico. Y para darles una idea, día a día nosotros utilizamos relojes atómicos. No directamente, por supuesto, pero indirectamente. Eso es debido a que dentro de los satélites GPS hay relojes atómicos. Y esto es necesario para poder regular y sincronizar todo el flujo de información que llega a ellos. Entonces, para poder sincronizar todas las telecomunicaciones, día a día es necesario que el reloj atómico sincronice muy bien el tiempo. Esto es debido a que para poder controlar muy bien el tiempo es necesario tener un oscilador que sea muy preciso y que sea muy exacto. Y esto es exactamente lo que es un reloj atómico. Entonces, en una primera parte me gustaría explicar cuáles son los ingredientes que andamos buscando en el desarrollo de un reloj atómico. En una segunda parte me gustaría explicar cómo hacemos esto en el laboratorio. Y en una tercera parte me gustaría explicar un poco qué es lo que he hecho durante mi doctorado. Entonces, ¿cuáles son los ingredientes que andamos buscando para desarrollar un reloj atómico o un oscilador ideal? Entonces, queremos primero un oscilador que sea el mismo sin importar dónde nos encontremos. Es decir, que sea el mismo en Latinoamérica, que sea el mismo en Europa, o sea el mismo en China, o hasta en Marte o en la Luna. Que sea el mismo o que podamos caracterizar muy bien cómo cambia de un lugar a otro. El segundo ingrediente que andamos buscando es, para poder controlar muy bien el tiempo, queremos que la frecuencia de oscilador sea muy alta, ¿sí? Y el tercero es que queremos estar seguros que medimos muy bien esa frecuencia y por eso queremos un oscilador cuyo ancho de banda sea muy fino, ¿sí? Entonces andamos buscando esas tres propiedades. Y de ahí que el desarrollo de la física atómica nos dio el oscilador ideal. Esto es debido a que los átomos son los mismos, no importa dónde nos encontremos. Y la física atómica nos enseñó que los átomos tienen niveles de energía que pueden ser excitados con frecuencias fijas, ¿sí? Entonces, para poder excitar esas energías es necesario una frecuencia única, fija, cuyo ancho de banda es muy bajo. Y esto nos dio el oscilador perfecto, ¿sí? De ahí que se desarrollaron los relojes atómicos. Una vez que teníamos estos ingredientes bajo control, el segundo paso es empezar a ver cuál especie de toda la tabla periódica nos puede dar un reloj aún mejor. De ahí que empezaron los relojes ópticos. Los relojes ópticos son un tipo de reloj atómico, pero que utiliza especies cuyas transiciones de excitación tienen frecuencias en el visible. De ahí que se llaman ópticos. Es decir, que tienen frecuencias que son mayores de 400 THz y tienen anchos de banda muy, muy finos, ¿sí? Por supuesto, para poder alcanzar este desarrollo es necesario que la tecnología exista para poder trabajar con este tipo de especies. De ahí que es necesario desarrollar lo que nosotros llamamos enfriamiento de átomos y tener los láseres y la tecnología para poder excitar esas transiciones y después la tecnología para poder medir a qué frecuencia están oscilando esos láseres y tener todo el tipo de control para poder comparar los relojes a través del mundo, ¿sí? Y básicamente eso es lo que he estado desarrollando durante mi doctorado. Entonces, ¿cómo hacemos esto en el laboratorio? Para poder trabajar con estas transiciones, lo que trabajamos en mi grupo es con iones, ¿sí? Un ion es un átomo al cual se le arrancó un electrón. Esto hace que se vuelva eléctricamente cargado y entonces lo podemos atrapar en una trampa electromagnética, que es un tipo de trampa que está oscilando así, que hace que mi ion se quede atrapadito como una caja de huevos, ¿sí? Una vez que lo tenemos ahí, usamos otro láser que lo que hace es excitar la transición muy, muy rápido y emitir muchos fotones, lo que irónicamente lo enfría. La analogía de esto es, si tenemos una bola de boliche y le tiramos muchas bolas de ping pong, eventualmente logramos que éste se enfríe. Una vez que el ion está atrapado, lo que hacemos es utilizar otro láser para excitar la transición del reloj, ¿sí? Y lo que hacemos es hacer un barrido de la frecuencia y buscar en qué punto tenemos más emisión de fotones para entonces encontrar la frecuencia exacta a la cual se excita esa transición y con esto tenemos entonces el reloj, ¿sí? Entonces, en mi grupo de investigación, en mi proyecto, trabajamos con dos tipos de iones. Trabajamos con iones de calcio y iones de aluminio. No lo mencioné al principio, pero en mi grupo somos especialistas en iones de calcio. Los demás experimentos y grupos dentro de mi grupo se especializan más en lo que es el desarrollo de computación cuántica, no tanto en metrología. Pero en mi experimento estamos trabajando en metrología con iones de calcio. El ion de calcio tiene la ventaja, como dije, que somos especialistas y tenemos mucho conocimiento en cómo enfriar los iones y atraparlos, y la tecnología se ha desarrollado para eso. Entonces tenemos las trampas de iones, las conocemos muy bien, las podemos construir. Los láseres los tenemos de muy fácil acceso. Tenemos una compañía que nos desarrolla todos los láseres que necesitamos y tenemos mucho control de la estabilidad de estos. El control está a tal punto ahora que tenemos una compañía dentro de nuestro grupo de investigación que está desarrollando ahora trampas que pueden ser controladas por cualquier persona y con solo, la idea, objetivo final es que con solo estripar botones, así como en un computador normal, podamos atrapar los iones y empezar a hacer procesos, ¿sí? El ion de calcio entonces tiene esa ventaja, que es muy fácil de trabajar, de enfriar, y tiene una transición de reloj que es muy buena. Está en la longitud de onda de 729 nanómetros. Y tiene la ventaja de que tiene un decaimiento de 1 segundo. Entonces tiene un ancho de banda del subhertz. Sin embargo, tiene la dificultad de que se ve afectado mucho por el medio ambiente. De ahí que el otro elemento con el que he estado trabajando es con el ion de aluminio. El ion de aluminio tiene la ventaja de que tiene una transición de reloj que es de muy alta frecuencia y que tiene un ancho de banda aún menor, pero tiene la dificultad de que el enfriamiento no es tan fácil. No hay láseres que nos permitan enfriar fácilmente este ion, y si quisiéramos hacerlo tendríamos que trabajar en vacío, lo cual hace que sea todo muy complicado. Entonces, en el 2005 desarrollaron una idea brillante en la cual que se llama enfriamiento simpatético. La idea es que por medio de otro elemento vamos a enfriar un elemento que no podemos enfriar tan fácil. Entonces, en nuestro laboratorio, ¿cómo funciona? Utilizamos el ion de calcio que podemos enfriar muy fácil y vamos a enviar un ion de aluminio en la trampa. Y entonces, por medio de la interacción de ellos en la trampa, el ion de aluminio va a transferir al calor al ion de calcio y seguimos enfriando constantemente el ion de calcio y con eso eventualmente los dos iones se enfrían. Y de la misma forma vamos a excitar las transiciones del ion de aluminio y transferir la información al ion de calcio y hacer la lectura por medio de esa interacción que tienen ellos en la trampa. Y eso es lo que se llama en inglés Quantum Logic Spectroscopy, que básicamente es esa transferencia de información entre los dos iones. Y esto es lo que he estado desarrollando durante mi doctorado. Entonces, en una primera parte nos enfocamos en cómo hacer este enfriamiento simpatético y en tener mayor control de él. La segunda parte trabajamos en la excitación de la transición de reloj y en poder tener control de ella. En una tercera parte empezamos a estudiar un poco más el medio ambiente en el cual se encontraban los iones, porque descubrimos que al excitar la transición de reloj del aluminio, interactuaba con las pocas moléculas que quedan en el vacío en el cual se encuentra la trampa. Se me olvidó mencionar eso, pero todos estos procesos se ocurren en cámaras de vacío. Sin embargo, aún quedan algunas moléculas con las cuales interactúa el aluminio, y entonces hemos estado desarrollando diferentes técnicas para poder caracterizar ese medio ambiente. Una tercera parte, que es un proyecto en el que estoy trabajando hoy en día, es en cómo hacer mediciones de frecuencia absoluta, es decir, en poder comparar nuestros iones, nuestras frecuencias, con estándares que se encuentran en PTV, que es el Instituto de Frecuencia en Alemania, o con NIST en Estados Unidos, o con China, o cómo comparar nuestros relojes con otros relojes en el mundo, y lo que queremos hacer es por medio de GPS. Entonces queremos aprovechar eso que les mencioné al principio y utilizar los relojes atómicos dentro de los satélites GPS y comparar la frecuencia a la cual están oscilando estos con nuestros iones, y si hacen lo mismo en otro instituto, es exactamente lo mismo que comparar ambos relojes y con eso tener mediciones de frecuencia absoluta. Para darles una idea, el objetivo final de nuestro laboratorio, de nuestro proyecto, sería utilizar el conocimiento de información cuántica, de computación cuántica que hay en el grupo para el desarrollo de relojes. Es decir, este es un proyecto que no se ha realizado aún, pero la idea sería usar esquemas de información cuántica para hacer lecturas de frecuencia. Y con esto espero que tengan muchas preguntas y muchas gracias por su atención.
That was a lovely talk from Elena. We're going to have questions all at the end after our second talk. And so I'm now going to introduce you to our second speaker, Liz Hernandez. She's an electronic engineer with a degree from La Universidad Distrital Francisco José de Caldas and has an MSc in electronic and computer engineering in the field of biomedical engineering from the Universidad de los Andes in Colombia. She has experience in the areas of control, automation, metrology, and she's the head of the Time and Frequency Lab at the National Metrology Institute of Colombia since 2014. And with that, I'll leave you to enjoy her talk. Thank you.
América Latina en Foco.
Hello, everyone. It is a pleasure to greet you from Bogotá, Colombia. I thank the organizers of this America Latina en Foco webinar series, especially Lacey Glasscock and Hermes Kamimura. I also thank Dr. Andreas Bauch, who is the head of Time Dissemination Group at PTB, which is the National Metrology Institute of Germany. Thank you for proposing my name as an expert in the field of time and frequency metrology in Latin America. Welcome to my talk, related to a look at the history of internationally recognized Colombian time scale UTC INM. This presentation is structured as follows. In the first part, I will talk about introduction, achievements, and team members. Then, the second part is related to characteristics of the time scale in Colombia. Finally, I'll go on to talk about international cooperation, conclusions, and future work. I have worked in metrology since 2008. So I have the honor to tell you important details of the last 13 years in the history of the Time and Frequency Laboratory in Colombia. The Colombian legal time is generated from the National Metrology Institute of Colombia, the INM by its Spanish acronym. The INM is located 2,600 meters closer to the stars. That means it's located at Bogotá in the eastern side of the Andes Mountains, approximately in the center of Colombia country. In this slide, we can see the slogan created in 1998 and an example of the current logo image used as the city brand. In February 2015, the first calibration and measurement capabilities, the first CMCs ever published for the history of Colombia, was obtained as international achievement. There were 13 CMCs in the quantity of time and frequency published on the website of the key comparison database KCDB of the International Bureau of Weights and Measures, the BIPM for its acronym in French. In September 2017, Colombia began its contribution to the generation of Coordinated Universal Time, the UTC. That is, 5 months before March 2018, and thus the INM was an active member of the celebration of 30 continuous years of publishing the Circular T as documentary evidence of the technical competence of each NMI that contribute month by month to the creation of an international time reference. Now, I want to describe a little about the team members of the Time and Frequency Laboratory. On the left side are my colleague Nelson Bahamon and I. With him, it was possible to achieve the contribution to UTC in 2017. On the right side, there are new colleagues, younger metrologists, each with a specific mission, and they are very supportive for the continuous improvement of the laboratory. Daniel Sotelo leads speed measurement topics. Fernanda Rodriguez contributes to the technical innovation of the legal time, and Alexander Gutierrez leads research topics in the laboratory. The standards and auxiliary elements are other team members. They are key devices for disseminating legal time and for providing calibration services. In the sequence of photos from left to the right, we can see the evolution of the facilities and the new standards acquired. Interestingly, metrology in Colombia began in 1965 with equipment donated by cooperation from the PTB of Germany. And today I am in this talk thanks to my colleague, Dr. Andres Bach, also from PTB. The important thing to visualize is that evolution had depended on a single cesium clock. If the clock is high performance, its lifetime is around 5 years. Or if it is standard performance, the time is up to 10 years. Therefore, on the slide, red text indicates that these cesiums are already out of operation. However, we highlight in blue the redundancy that we currently have 3 high-performance cesium clocks and 2 NTP servers. What is highlighted in green letters indicates the names of the devices donated by the National Institute of Standards and Technology of the United States. That means by the NIST to implement international comparisons, one at the American level, led by the Inter-American Metrology System, the SIM, and another at the international level to contribute to the UTC led by the BIPM. Let's turn to the next 3 issues. First, how UTC INM came to existence. I will explain how we could publish CMC before contributing to UTC. The most common is that a country has its own National Metrology Institute. However, in Colombia, the metrology area was within a government entity that has consumer protection functions until 2011, when the INM of Colombia was created, and in 2012 started its operation as an independent entity. In the transition, the commitment to demonstrate technical competence through international accreditation was inherited. A United States accreditation body was selected. National Voluntary Laboratory Accreditation Program, the NABLAP, carried out the first audit in 2013. In that same year, the INM signed the Mutual Recognition Agreement of the International Conference of Weights and Measures, the CIPM MRA. Also, in 2013, the Time and Frequency Laboratory of the INM achieved the approval of its quality system by the SIM. Let us remember that the SIM is the regional metrology organization in America. In the period of time from 2014 to 2015, work was done to publish the first CMCs in the KCDB of the BIPM. For this, the list of comparisons that support the technical competence and the validity of the results is a great importance. The first tool was the time scale called SIM Time Network, the SIM-TN. In this regional comparison, the NMIs of America participate, and some of them simultaneously contribute to UTC, such as the United States, Canada, Brazil, and Mexico, among others. Thus, the way to demonstrate technical competence of Colombia was through the SIMT comparison, using the United States NIST as a pivot to obtain a statistical analysis of results with respect to UTC. The end result was the publication of the first CMCs for the history of Colombia in February 2015, as I mentioned in the introduction. I had also mentioned that in September 2017, the INM appeared for the first time in a circular T, which was the number 356. To build the UTC INM time scale and link it as the main comparison list that supports the published Colombian CMCs, it was necessary to go through the SIM approval of the quality system in 2018. And as evidence to demonstrate continuous improvement through the results of follow-up accreditation audits, at least once every 2 years since 2013. Let us remember that 2018 was the celebration of 30 years of continuous publication of the Circular T month by month. After this sequence of international recognition events, the INM no longer binds the laboratory accreditation, but implements peer review to execute the audits that demonstrate compliance with technical competence requirements. As everything is framed in the structure of quality and periodic monitoring, the year 2023 is approaching to present again our time and frequency quality system for the SIM approval. But you can see that I didn't speak of the year 2016. So I'm going to talk about what was implemented in infrastructure between the years 2015 and 2017. It was necessary to characterize the most exact location of the antennas from the two international comparisons, the SIM and the BIPM comparisons, to contribute to the SIM-T and UTC time scales, respectively, as well as the wiring and auxiliary elements adjustments. The necessary measurements of heights and distances between the two antennas were made. For the SIM-T INM scale in 2015, a contribution percentage of approximately 3% was obtained, and after characterization, consistency was achieved with the UTC INM scale in 2017. In particular, the SIM time network comparison system was donated by NIST to Colombia before 2011, that is, before the INM was created, and had an updated system in 2015. Then, between 2014 and 2015, the entire administrative and technical process was carried out to the donation of the system that allows data to be sent to the BIPM, and after achieving data consistency, a long period of observation and adequate configuration of the system, then it was able for the INM to appear in circular T. In the field of time and frequency, the objective of all NMI or designated institutes DIs is to contribute to the UTC month by month through the circular T. I have explained how it starts with audits that can be executed through an accreditation body or a peer reviewer. It is important to highlight that the year of execution of each activity is left on the slides as an example as black and white rectangles because it depends on the administrative elements of each country. The only specific period of reference that I present in the slides is the period of every 5 years of SIM approval of the quality system. Let's move to the second issue, how UTC INM is generated. The current traceability scheme is presented here. The diagram of the laboratory setup shows the synchronization between two cesium clocks using a 1 pulse per second, 1 ppm signal in a modular way. A 5 MHz frequency output signal from each clock is connected to inputs A and B of a switch and distribution unit. A 5 MHz output from this device is input to an auxiliary output generator, an AOG, also known as a microphase stepper. From this AOG, a 1 pulse per second signal is obtained, which is connected to a pulse distributor amplifier. At this level, one 5 MHz signal and 1 ppm signal make up a set of inputs to each of the international comparison systems. 1 ppm signal constitutes the UTC-INM time scale, and the other ppm signal constitutes the SIMT-INM time scale, whereas the 5 MHz signals become the time-based reference for each system. For the SIMT, you can see numerical and graphical results published daily on the website created by NIST. For UTC, the circular T is obtained at the end of each month, sent by the BIPM. For each connection and configuration, it was necessary to implement the measurement of the cable delays. The third issue, how UTC-INM serves two purposes in Colombia. Most citizens perceive reliability in event dating not directly from the INM, but from some other entity in the country within the framework of the quality infrastructure, and should take the INM legal time as a reference. Another purpose is to provide metrological traceability to secondary laboratories through calibration services with international recognition of its CMCs in time and frequency. In addition, we have realized that legal time is a key tool to promote digital transformation policies in the country, which will allow future technical regulations to be configured. Regarding the legal time in the INM, we have configured a free metrological product and a paid service. On the slide left side, we list the free access modes, the URL, the public IP, and voice signal via telephone. On the slide right side, we can see 5 service groups offered by the Institute. The Time and Frequency Laboratory created one service related to metrological measurement called Measurement of Synchronization Offset with Legal Time, inspired by the comparison systems to obtain the SIMT and UTC time scales. Then, a personalized application known as Premium Legal Time was created, and different socialization webinars were held in 2020. Regarding scientific publications, we are beginners. We have a publication of the state of the art of legal time published in 2016. The most recent publication of this 2021 is an achievement of my team members' colleagues as adjunct metrologists who were winners for the Andemet region of the event SIM Early Career Metrologist Award. Finally, I'd like to end by emphasizing the main points related with international cooperation. I would like to address the key stages of knowledge transfer from SIM and Euramet colleagues to obtain the achievements presented. First, NIST donated the International Comparison System activity led by Mike Lombardi in 2007. In 2009 and 2010, the opportunity to exchange technical concepts and statistical analysis validation methods with Francisco Jimenez from CINAM of Mexico and Oscar Fallas from ICE of Costa Rica. Then, my first steps of setting up the SIMT-INM scale with Mike Lombardi and solving CMC estimation doubts with Dr. Andreas through a short one-week visit at the PTV facilities in Germany. Next, again, Mike Lombardi appears transferring knowledge to configure the UTC INM scale, and I had the opportunity of a guest researcher stay at Nice, having Stefania Romisch as my direct boss, which resulted in the beginning of the contribution to the Colombia 2 UTC. After that, in 2017, Mauricio Lopez from CINAM and Mike Lombardi were peer reviewers. They were the first two chairs of the SIM Time and Frequency Working Group. Currently, the INM participates in collaborative work between Raúl Solís from CENAMEP of Panama as last chair and Diego Luna from INTI of Argentina as the new chair of the group, with the constant support of Dr. Marina Gertzwolf from NRC of Canada. Finally, at INM, we had the honor of hosting the last face-to-face group meeting in 2017 about conclusions and future work. To sum up, my presentation was focused on two major issues: the UTC INM and the international cooperation. There are 5 elements involved. First, the national sovereignty to generate the legal time. Second, transfer international confidence for dating events in several activities in the country. Third, implement a constant verification of the synchronization status of organizations that use the INM legal time as a reference. Fourth, reliability by making use of new technologies. All of these elements are reflected in fair economic transactions and the identification of improvement opportunities. Conclusions. Contributing to UTC puts INM of Colombia in the context of all the institutes that have demonstrated technical competence in the field of time and frequency. The state-of-the-art of the INM of Colombia is a step-by-step tool for colleagues from other institutes of the SIM of America who still don't contribute to the UTC. INM of Colombia creates the first 24/7 Internet remote measurement with the design of a customized application as a metrological confirmation activity for companies that use the legal time as a reference. Future work. In my opinion, we should create opportunities for improving the contribution of UTC INM to UTC and start contribution to rapid UTC. Create services, categories of satellite remote calibration to generate metrological traceability to users who require high accuracy of the Colombian legal time. That concludes my talk for today. Thank you for your attention.
Okay, thank you, the speakers. I will just explain one more time the interpretation. At this moment, the interpretation is available live in Spanish or English, depending on the languages spoken here. Just to make sure you use this feature correctly, if you understand Spanish and English, you can just switch off. So you understand that that's just us, not the interpreter. Otherwise, one of the volume, if depending on the language you choose, one of the volumes will be down. So you won't hear the other person, just the interpreter, okay? Hopefully this is clear. Lacey, please.
Thank you, Hermes, for that. I would now like to introduce you to our technical moderator for our 5th webinar, which is Dr. Marina Gertzwolf. She is the team leader for Frequency and Time Group at NRC and is responsible for realizing the 2nd and SI unit of time and for maintaining and disseminating the official time for Canada UTC and RC. So thank you so much, Marina, for joining us today. We're so happy to have you.
Thank you very much, Lacey. And I want to thank Milena and Liz for excellent presentations. It was very well done and very engaging talks with a lot of information to process. And I wanted to make a point that if you thought that developing optical frequency standards is difficult, what Milena has presented, you now have a good impression of how difficult it is to have CMC's measurement capabilities and the UTC timescale developed in the country and recognized. In Lee's presentations, you could see how many people, different organizations are involved in this work. And so excellent work, both Milena and Liz. I congratulate you both. So I invite the attendees to present questions, and the questions can be presented in chat. They can be typed, then I can read them. And if you have questions that you want to ask live, please indicate this in chat, and Lacey or some other people that helping run the seminar will be able to unmute your microphone and invite you to speak. So please start with your questions to have some initial discussion ongoing. I would like to ask Milena first. Your description of an optical frequency standard has been very interesting. I have a question. What specific part of this is a big research project. So what is specific part of the research project that you work on that maybe you can give us a little more insight about the little smaller bits and pieces that you are responsible for in the project?
I'm actually responsible for the whole thing.
Okay.
Yes. Yeah. So yeah, I joined the experiment when the experimental setup was already built in the initial state. So they were already able to trap aluminum ions, which is a bit more complicated than the usual, as I explained before. And then basically, so what I worked was in repeating the measurements of the first observation of the aluminum transition, which is what I presented before. And then I was working in the development of these techniques to characterize the background. And this year I worked in the characterization of the calcium transition. But yeah, so yeah, I work, as I said, with Christian Ross and Rainer Blatt, but in the experiment in the past 4 years, it's been just me, yeah.
Okay, well, thank you. This is very, very impressive. And
I mean, I'm in a very big group, so every time I need help, I ask some of my colleagues. But in the experimental setup, yeah.
Well, excellent, and congratulations on that. I can appreciate how complex and large the systems are. And so a follow-up question then. The optical frequency standards have surpassed the microwave frequency standards that are used currently for the redefinition of the second. Do you see your research work as part of the groundwork for the new definition? Do you think the specific clock you're working on is a strong candidate, or can you speak please about the optical standards for the next generation of SI second?
Yeah, so at the moment, the aluminum, not in our lab, but in other groups, especially in NIST, is one of the best optical standards. So it's reaching, just to give you an idea, 10 to the minus 18, or low to the minus 18, so 10 to the minus 19 even. And so there are two kinds of clocks, right? So you have ion clocks, so would you have the aluminum and also the ytterbium at PTB, or at PTB, basically that are the best ions in the world, I would say. And then you have also optical lattices, which is a bit the same idea, but you have many atoms in the clock, right? And this one, they're also reaching also low to the 10 to the minus 18 and 10 to the minus 19, I will say. And this is more with strontium. So I would say that the work with aluminum might be, it steps forward to the next definition. But what we are focused more in my group, we don't want to compete with PTV or NIST or any of this. We don't want to develop necessarily a new standard, but what we want is to collaborate with techniques on how to do precision measurements. So as I mentioned before, we are in my group, most of the people work more with entanglement and quantum computation. So the idea will be to develop techniques to be able to improve these clock measurements. So basically that's a bit the direction of our experiment.
Well, that's very interesting because with entangled ions, you probably can achieve even better stability and even lower uncertainties than you can right now. So that's very interesting work. Thank you. Thank you, Milena. I would like to ask Liz, because I don't see questions coming up yet. You presented, Liz, an extensive work on the development of Colombian official timescale, UTC-INM, and your development of your calibration capabilities. What do you see as your immediate next steps? You mentioned some in your conclusion, but maybe you can be more specific about what are the next steps, how you're going to enhance your services or your measurement capabilities.
Okay. Hi, Marina. One specific activity now is to improve services related to satellite measurements. That is one, because now, since 4 months ago, the new director of the institute was my first boss here in Time and Frequency Laboratory. So he knows a lot about the field and he wants to develop that. It is the main step. And with that, that will be the first step to publish a new CMC related to that kind of measurement. So it's the link of the two activities.
Okay. Thank you, Liz. I wonder if in Colombia you face the concerns that there is now in industry and the government with heavy reliance on GNSS signals, on GPS, Galileo, GLONASS, and other constellations for positioning, navigation, and timing. For us, of course, for our community, it's timing. Do you face the same concerns, and do you build or do you investigate alternative measures, alternative solutions that will mitigate the vulnerability to GNSS signals jamming and spoofing?
No yet. No, we need to put that activities in our plan next year, because we will just begin with a prototype of measurements with what we have available. The GPS for sure will be the first step to include the first tool to include in the measurements in the prototype. So we will talk about that. Yeah.
Okay. Well, thank you very much, Liz. I invite attendees to ask questions. I don't see any hands raised or questions in the chat. I guess the presentations were very clear. Please don't be shy. Even if you're new to the field of frequency and time metrology, it's a very complex field, as all metrology is, but it serves the measurements in all other fundamental units. So we're very proud of this role in time and frequency. And I wanted also to point out that notice it's not just Latin America in the focus today. It's women of Latin American research field that are in the focus. So I congratulate Liz and Milena as a very strong female scientists that really move forward the science in their respective regions, and we're very proud of this work done in our SIM region. Any questions? Well, Lacey, if there are no questions, I think we can thank the speakers.
Yes, of course. Thank you so much, Milena
Again.
and Liz and Marina, for all of your help for today's webinar and for the Latin America Outreach Initiative Organizing Committee for this year of webinars. It's been a wonderful experience. So stay tuned for 2022 as we continue this initiative and these videos. We look forward to providing more educational content.
Thank you very much, Lacey. I just wanted to make a note, maybe you mentioned it before, these videos have been recorded. So those who attended today and found this interesting, please send links to YouTube recording of these videos to your colleagues and friends, so we can have a big audience enjoying this presentation.
Yes, the YouTube recording will be available next week for viewing in case you missed it or in case you want to share these wonderful talks with our speakers.
Okay, well, thank you all again very much.
Thank you, everyone, and have a wonderful day.
Thank you.
Happy holidays, everyone.
Happy holidays.